Welcome back. Our discussion on solutions now brings us to double replacement reactions, or actually limiting reactants. I know that limiting reactants can be challenging for a lot of us, so make sure that while we're going through this process, and there's a lot of good review in this whole process, make sure that if you feel like you're weak in any one skill that we see here today, that you just make sure you take some time to really focus in on that and get stronger in that particular area. Ask a friend, ask me. Make sure you're comfortable with everything that we're going to be covering in this particular section. But it's important to know what's going on here because we need to be able to do this particular process for a lab that we're going to be doing very soon. So let's check it out. We are going to be dealing with double replacement. It says that suppose we have 25 milliliters of a solution containing 1.23 grams of, I'm going to fill in the blanks, zinc nitrate, and it's mixed with 30 milliliters of a 0.355 molar solution of sodium hydroxide. And we are going to do a lot of different things with this. So let's start small. We're going to kind of take this in pieces and then put it all together in the end. So let's first calculate the molarity of zinc in the nitrate solution. Now I'm going to be taking my time on this. If you're really comfortable with limiting reactant, you can probably blow through this pretty quick and just kind of get what you need out of it. But if you're not comfortable with the process, like I said before, I really encourage you to focus in on the parts of this that you don't feel comfortable with. All right, so let's start by calculating molarity. So we talked about in our previous video that molarity is moles over liters. Now we don't have moles, but we do have grams of zinc nitrate. So I can take the grams of zinc nitrate's going to look like this. If you're not comfortable with writing out formulas, it's something to keep in mind, right? Zinc has a +2 charge, nitrate has a -1. When I balance those things out, I have to have a ratio of 1 to 2 in order to give myself 0 on the overall charge. Just remember. And I'm going to convert that zinc nitrate into moles of zinc nitrate. I'm going to be doing that using molar mass. If you want to take a second and practice calculating molar mass yourself, I'd really encourage you to do so. You know, go into the periodic table, punch up what the molar mass is for zinc nitrate. But what you should get is what you should get is you should find that the molar mass of zinc nitrate is not 18, it's 189 grams per 1 mole of zinc nitrate. Now I'm going to do this all in one shot, but you are of course welcome to calculate those moles separately and then divide these by the liters which are given in the problem. They give us 25 milliliters. Let's not consider the whole volume yet. We're considering the two different solutions are separated right now. So we have 25 milliliters. So we are going to use liters like this. Now be careful. Notice that I added that 0 there. You might think, well, why did you add that 0 there? Whenever I convert between, liters to milliliters or milliliters to liters, I need to make sure that I retain the same number of sig figs. In the beginning of the problem, I have 25.0 milliliters, which is 3 sig figs. So when I convert that into liters, I need to make sure that I keep those same number of sig figs. Parentheses right there. And I'm going to calculate this. If you'd like to pause and punch this up yourself, you go right ahead. But you should get 0.26 molar. That should be our concentration. And that would be molar of zinc nitrate. So be sure to label it. I don't have room to label mine, but make sure you label yours. That was easy. Let's keep going. We're going to now write the balanced net ionic equation for the dissociation of zinc nitrate. So remember that when we have a dissociation equation, we are going to take the ionic solid, which is the zinc nitrate that we've been dealing with, and we are going to show it as a solid, and we are dissolving it in water. So we're showing a reaction. It's not really a reaction. We're showing a chemical equation, but we don't include the water. Remember, all we do with dissociation is we take the ionic solid and we break it apart into its ions. So that's made out of zinc and that's made out of nitrate. Be careful, don't break the nitrate apart. Remember that nitrate is a polyatomic. It's got to stay together. We need states of matter. Always, 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 ions are aqueous. And then we need to balance this. So it's actually really easy to balance. We just put a 2 right there. We did it. That's a dissociation equation. Now let's write a double replacement reaction for the equation that occurs. So we know that we're dealing with zinc nitrate. This is again, nice review because now we're practicing our balancing chemical equations. And we're dealing with sodium hydroxide. So we are mixing this with sodium hydroxide, also aqueous. And we are going to go through double replacement. Now remember, with double replacement, we're switching dance partners. A positive thing goes with a new negative thing. A other negative thing goes with a new positive thing. So we are switching dance partners. Zinc is going to go with the hydroxide. Sodium is going to go with the nitrate. Let's put the arrows like this, just to show the order that we're going to be doing. Now remember that the easiest thing to get yourself mixed up with double replacement is that it's really easy to just start writing the subscripts the same way on both sides of the equation. But don't do that. Just think to yourself, what is it that you're making? So sometimes it's easier to just say it out loud and then just write it without even looking at the left side of the equation. For example, I'm going to do sodium and nitrate together. When I write that, that's a 1-to-1 because sodium has a +1, nitrate has a -1. I'm not even going to look at the other side of the equation. I'm just going to write sodium nitrate because I know that's what sodium nitrate is supposed to look like. And it's aqueous because of my solubility rules. Remember, I told you got to polish up on your solubility rules. Make sure that you're doing that. Now I'm going to mix zinc hydroxide. So zinc has a +2 charge. My Z's have been really bad. That's a little better. And my hydroxide has a -1 charge, so it looks like this. And based on my solubility rules, hydroxides are often insoluble, so it's going to be a solid. Now we're not done yet. We have to balance this. We're going to, if you want to take a second to quickly balance it, make sure that you do. You should get 1, 2, 2, 1 after you're balancing. All right, so that's 1 zinc nitrate, 2 sodium hydroxides, 2 sodium nitrates, and then 1 zinc hydroxide. So let's keep going. Let's write the balanced ionic equation for the reaction that occurs in C above. So that means we're going to keep our eye on the balanced chemical equation. And remember that what we're doing here is we're taking everything that's aqueous and we're breaking it apart into its ions. That's all an ionic equation is. So it's just like dissociation like we did before, except now we're doing it for everything that is aqueous. Don't forget that as long as it's an ion, oh, that's not a +2, it is aqueous. I always like to say that this isn't hard work. This is just wrist work. It doesn't actually take a lot of effort to be able to do this. It just takes time. But once you get fast enough at it, it's no trouble at all. Don't forget to balance this. So you could balance it based on the balanced chemical equation at the top, but it's kind of easier just to balance it at the end. So if I look here, I see that I have 2 hydroxides on the right. I'm just going to kind of cram a 2 in there, and then it's balanced. Now let's go ahead and write the net ionic equation. So remember with the net ionic equation, all we need to do is take out the spectator ions from the ionic equation. So we can actually do E and F kind of at the same time. The spectator ions are the ones that appear identical on both sides of the equation. So we're saying that the spectator ions in this situation have to be Na plus and NO3 minus. The only difference between this and the net ionic, or the ionic and the net ionic, is that we just remove these things. So we have zinc reacts with hydroxide. We have 2 of those still. Gives us zinc hydroxide. And there are 2 of them. And that's it. That's how you write the balanced net ionic equation. So all you do is remove the spectators. It's really straightforward. Now let's get to the actual limiting reactant part. So now we have to figure out the limiting reactant. Remember that when we try and figure out limiting reactant, the first thing we want to do is get moles of both. We want to get the moles first. Because remember, if we know the moles, we can compare the moles. And then we can figure out the ratio, okay? So let's do that. So we kind of already did this before. Maybe you already have this number. I did not do it before, so I'm going to write it out again. But I'm going to take the grams of zinc nitrate that I started with, and I'm going to use that molar mass again. And that's zinc nitrate. And I'm going to take the moles of zinc nitrate. And I'm going to use those to find moles. So like I said, this was kind of a process that we did before. It should be 0.0651 moles of zinc nitrate. Now, as far as finding the moles of the sodium hydroxide, we are given different things in the problem. So if you look up at the problem, you notice that it tells us the liters, or in other words, the milliliters of the sodium hydroxide, excuse me. And it also tells us the concentration. Now remember, in our previous video, if I go through this, I'm canceling out liters here, and the thing that I'm left with is moles. So this will actually, multiplying these two things actually successfully gives me the moles of sodium hydroxide. Now, I know the moles of both. Remember that the thing I'm going to do is I'm going to set up the bunk beds. I'm going to put big sibling on top, little sibling on the bottom. And I'm going to use that ratio to figure out how many moles of these two things I have available to me. Because remember, I'm trying to figure out how many moles I have available so I can compare them to how many moles I need. So the bigger one here in this situation is NaOH. So NaOH goes on the top. Make sure you label, because if you don't label, sometimes we can get confused about which one's which. So we have NaOH on the top, we have zinc nitrate on the bottom. And when we do this ratio, we should find that we have 1.6 NaOH to every 1 zinc nitrate, which I don't have enough room to write that. So every 1.6 to 1 zinc nitrate. Now if we look back at the balanced chemical equation that we wrote before, for every 1, again, for every 2 moles of NaOH, we have 1 mole of zinc nitrate that's required. That's based on the balanced chemical equation. So we need 2 moles of NaOH, but we only have 1.6 available to us. Therefore, the limiting reactant is NaOH. And the limiting reactant controls the problem. As soon as I run out of limiting reactant, I run out of everything. So I use the limiting reactant to determine how many grams of precipitate should form. First, you should ask yourself which one's the precipitate. The precipitate is zinc nitrate. So I'm looking for grams, or not zinc nitrate, but zinc hydroxide. That's what I'm looking for. So let's find that. Let us take the moles of NaOH that we started with, 0.106 moles of NaOH. And we are going to use the balanced chemical equation to convert to what we're looking for. So we know that we have 2 moles of sodium hydroxide from the balanced chemical equation for every 1 mole of zinc hydroxide from the balanced chemical equation. We're going to use molar mass again, but now we're using the molar mass of zinc hydroxide. Again, if molar mass is something that gives you an issue, I would encourage you to go back and try and find that molar mass, but I think it's 99.4 for zinc hydroxide. Calculate this, we should get 0.527 grams of zinc hydroxide. And that's it. So that's how we do limiting reactant. We have to find the ratio first, and then we use the limiting to determine what we want. Now let's say that we have this reaction that's carried out, and we actually have, this is a typo here, so please make sure that you correct this in your notes. This should be 0.495 grams. Now we want to determine percent yield. So remember that percent yield is experimental divided by actual, so the experimental amount that we calculated is 0.495 grams. The theoretical is the value that we have up here, so that's that 0.527. So I'm going to take that 0.527 grams, and it is a percent, so I'm going to multiply it by 100, which gives me a percent yield of about 93.3%, which is pretty good. That means we did pretty well on this experiment. Percent error isn't as useful. It really more tells us how bad we did, but percent yield is a little bit more valuable as far as a unit. So we remember that percent error is theoretical minus actual, or actual minus theoretical. It doesn't really matter because there is an absolute in that. There can't be a negative. So, and that's going to be divided by the theoretical. And again, that's multiplied by 100. And that gives you 6.1%. Now really be careful with your sig figs here when you're doing percent error. It's like the trickiest part. Make sure that you handle these sig figs. It's a mixed operation. So you're going to do the subtraction first, and then you're going to do the division. Remember that the subtraction is based on the precision. So luckily these both have 3 sig figs as far as precision. And then you're going to do the division, which you should find that you only have 2 sig figs by the time you're all done. Okay, so that was the whole process, and now I'm going to give you a chance to run through that process on your own. So first thing I'm going to do is I'm going to help you fill in all these blanks, and then I'm going to give you that time to just go back, and we'll go over each one. So we are now talking about Let's see. I gotta flip my page here so I can know what the blank is. We're talking about aluminum nitrate this time. I gotta write the word aluminum better. There we go. So aluminum nitrate is mixed with potassium hydroxide. We want to first calculate the molarity of the aluminum nitrate, and then we want to find the balanced chemical equation, or the balanced dissociation equation for the dissolving of the aluminum nitrate. And that one's all messed up, but should be fine. I think there is an error at the bottom again, so this shouldn't be 0.595 grams in the notes. Instead, this should be 1.95. So this should be 0.1995. There you go. You should be able to do the rest. So it's going to be the same as the process before. I really encourage you to give this a really good try. See how you do. I'm going to pause, or I hope you pause, and then I'm going to write out all the setup and solutions, and then we'll go over it, and then we'll be done. So come on back when you're finished. Good luck. Whew, it's a lot of work. Let's check to make sure that we did it right. So first I'm going to start by calculating the molarity of aluminum nitrate. I do it just like the first time. Take the grams of aluminum nitrate, convert them into moles of aluminum nitrate using molar mass, so these cancel. And then that's just moles over liters. That should give me 0.231 moles, or molar aluminum nitrate. Again, you're more than welcome to do the moles on another step and then just plug in. We're going to write the balanced net ionic dissociation equation for the dissolving. So we're going to take the aluminum nitrate, we're going to dissolve it in water. We get Al plus 3 NaO3 minus. Don't forget to balance. We're going to write the double replacement reaction. So remember that we are flipping partners here. So KOH is going to double replace with AlNO33. So we get KNO3, potassium nitrate, and we get aluminum hydroxide. Don't forget to balance it. 1, 3, 3, 1. Then we are going to write the balanced ionic equation. Remember, all we do is we take everything that's aqueous, we break it into its ions. I highlighted the spectator ion, so that makes the next step easier for us. The next step, we just write the net ionic equation by removing the spectator ions. Easy peasy. Okay. Then we're going to figure out limiting reactant. We already know how to figure out moles of AlNO3. We did it before. We do it again. We then calculate the moles of KOH from the values given to us in the beginning. We then compare that ratio. We have 1.8 KOH to every 1 aluminum nitrate. The balanced chemical equation says that we need 3 potassium hydroxides for every 1 aluminum nitrate. So that means the limiting reactant has to be potassium hydroxide. Take moles of potassium hydroxide because it is the limiting, and we are converting it into grams of precipitate, which is aluminum hydroxide. You should get 0.270 grams. And finally, we do percent yield. Not as good this time. We got a percent yield of 72.2. Mind your sig figs. Percent error. We have a bigger percent error this time. There's a 28% error. Again, mind your sig figs. And that's it. That's all it takes. We'll see you next time.